So when we were considering friction, we said that kinetic friction applied when an object was moving, and in that case we could use that the frictional force was equal to mu k times the normal force, and that if the body wasn't moving, then we should use the static friction case, in which case the frictional force is given by mu s times the normal force. Now, technically, this isn't 100% true. There's a little subtlety in it. So rather than being if a body's moving or not, we should actually be considering whether there is relative movement between the two surfaces involved. So with the example we looked at last time with a textbook sliding along the desk, there is relative movement between those two surfaces. So this is indeed a case where we use the coefficient of kinetic friction. Where it gets a little bit more complicated is where objects are rolling. So for example, if this ball rolls along the desk, then at the point of contact between the desk and the ball, there is not actually any movement. So for objects which are rolling, even though they are moving, we actually apply static friction. So practically, this is part of the reason why ABS brakes, which are anti-lock brakes, are so important on cars. So if a car is traveling along the road and it comes to a sudden stop, then it's the frictional force which is going to bring it to that sudden stop. Now, ideally for a car, if you throw on the brakes, you want the car to stop in as short a distance as possible. And so you want as much force slowing you down as you can possibly have. So the force which slows you down is the frictional force. So we're saying that when you hit the brakes, you want as much friction as possible between the road and the wheels of the car. Now, in the case where a car throws on its brakes suddenly, sometimes the brakes will lock. And so instead of rolling along the table, so let's just look at rolling. Here's rolling. If we put on the brakes suddenly, we can have a case where the wheels actually skid along the table like this. And in that case, there is relative movement between the bottom of the tire and the table. So you can see that relative movement. So in this case, kinetic friction applies. And the equation for the force which is slowing down the car is given by the force is equal to mu k times the normal force of the car. Now, in the case where the wheels are free to continue rolling, we then have static friction applied, and so the frictional force in this case can be as large as mu s times n, where mu s is the coefficient of static friction. And as we've seen, the coefficient of static friction, mu s, is larger than mu k. So in the case where the wheels continue free to roll, we have more force applied and the car can come to a stop in a much shorter distance, as well as the driver maintaining control over the steering of the car and where it ends up. So it's very desirable to keep the wheels on a car rolling when you slam on the brakes. So let's have a look at a little calculation we can do about this now. So the question, on a wet road, mu s is equal to 0.70, while mu k is equal to 0.35. For a car travelling at 60 kilometers per hour, calculate the stopping distance if the wheels lock, and again for if the wheels continue to roll. Okay, so in order to get the stopping distance, we're going to want to use one of the kinematic equations. The best one to use is v squared is equal to u squared plus 2as. S here is the displacement, so that will be our stopping distance. Since it's stopping, the final velocity is going to be 0. The initial velocity is equal to 60 kilometers per hour, which is equal to 60 times 1,000 over 60 times 60. So that's equal to 16.67 meters per second. And the acceleration is going to depend on whether the wheels lock or if they skid. Okay, so in the case when the wheels lock, let's do lock over here and skid over here.
we've got that the only force acting on the car is the frictional force. So that's equal to the mass times the acceleration. And if the wheels are locked, then they're skidding over the surface, and so it's mu k that we need to use. So that's equal to mu k times the normal force, which is mg. And so this tells us that the acceleration is equal to, the two m's will cancel out and we'll end up with mu kg. So we can use our kinematic equation, we can rearrange it and say, well, S is equal to u squared over 2a. I substituted in 0 for our v in this case, and then we should put the absolute value signs around here. The acceleration is in the opposite direction to the velocity, which is what we expect for friction because it always works to slow an object down. Okay, so now we can substitute in for our a. So we've got u squared is equal to 2 times mu k times g. Okay, let's substitute in values. So we've got 16.67 squared over 2 times mu k, which is equal to 0.35 times g, which is 9.8. And solving this, we get 40 meters. Now, for if they skid, we've still got the frictional force acting, so ma is equal to our frictional force, but in this case the wheels are still rolling, so there's no relative movement between the surface of the road and the wheel, so it's mu s times mg, where mg is the normal force. So this tells us that the acceleration in this time is equal to mu sg, and so we've got s is equal to u squared over 2 mu s g. And substituting in this time, we've got 16.67 squared over 2 times 0.70 times 9.8. And solving this, we end up with 20 meters. So you can see the car can come to a stop in a much shorter distance.